Hi, so we've been looking at bodies going at constant speed in a circle. What we have to bear in mind is that constant speed is not necessarily the same thing as constant velocity. Look, here's my body going at this point in the circle, and we know its speed is v, and we've been looking at something that maintains the magnitude of its velocity, so it keeps the same speed, but of course velocity has direction. But if we look at our particle down here, well, it is now going in a new direction. So we have to realise that something going in a circle at constant speed is changing velocity. The velocity is changing, and whenever you have a changing velocity, you've got an acceleration. Well, this is called the centripetal acceleration when it refers to when it's something going in a circle at constant speed. So, and it's given by the formula a equals v squared over r. So the centripetal acceleration is defined as a equals the speed squared divided by the radius of the circle. We ought to put the radius in there. There it is. Well, that's all very well. Where does this come from? Because it's not obvious at all. Well, you don't need to derive that in the exam, so I'll put that in a separate clip for people who are interested. But what we can see is that because v equals omega r, as we also found in the last video, then we can rewrite the acceleration in terms of omega. So we would have omega r squared divided by r, because v equals omega r, which simplifies to omega squared r. So we've got two possible expressions there for the centripetal acceleration. So to summarise, if a body is moving at constant speed in a circle, then it must be undergoing a centripetal acceleration, and that centripetal acceleration is given either by v squared over r or omega squared r. They're both the same. Bear in mind, it's just normal acceleration. The fact that it's called centripetal is just because it makes something go in a circle, but it's normal acceleration in the sense that its units are just meters per second squared, just like any other acceleration. Well, of course, if something does undergo an acceleration, then we know from Newton's second law, F equals ma, that there must be a force causing that. And so the fact that there is an acceleration means that there must be a centripetal force, something causing that change in direction. Well, it's worth just kind of trying to imagine what that force must be doing. Well, if we go back to our sort of circle over here, you can kind of imagine, if we look at position A there, and then, we've got to change its direction so that it starts to move in this direction a little bit later on in position B, for example. Well, you can kind of imagine that the force has to kind of be sort of to the right to kind of make that direction change happen. Well, again, it's not obvious, but it turns out that the force has to be always directed to the centre of the circle. So at position A, if I want to change that direction in such a way as to make it go in a circle, I have to sort of wallop it towards the centre of the circle. And the same at this next position, position B, I would also have to give it a clonk straight towards the centre of the circle, that's position B there, if I wanted to keep it going in a circle. So, as I said, not necessarily obvious, but kind of makes sense. It can be proved, but so the centripetal force, importantly, always acts towards the centre of the circle that the body is moving in. And of course, because F equals ma, we can write an equation for that. So we can say that F equals m times v squared over r, or F equals m omega squared r. So we can summarise that bit down here as well. The acceleration is v squared over r, and that's produced by a centripetal force equal to F equals mv squared over r, because F equals ma, or m omega squared r. And of course, that's just a normal force. It's just that it acts towards the centre of the circle and makes something go in a circle. And that's why it's called the centripetal force. So it's measured in newtons. So those are the first equations. We're going to use them real soon in the next clip.